Hey everyone, and welcome back to my Making a Coilgun series. Last episode I showed how we can use more coils to improve our launches. In this video, I'm going to use this optical sensor to create the double coil setup. Last episode I had shown off these optical sensors. They weren't really a good fit for the project though, since they're made for detecting remote control signals rather than constant on and off signals. I ordered these new sensors that should work better. These new sensors only have two leads and act like a variable resistor. Here I have my multimeter, and if I cover up the sensor to block any light from getting to it, and measure the resistance between the two leads, the meter reads a little under a megaohm. Now if I take this IR LED and power it up, we have an IR light source. If I keep my meter connected to the IR sensor and point it at the LED, you can see the resistance drops to a little under a kiloohm. So by pointing the light at the sensor, we made it 1,000 times less resistive. If we had some way to detect a change in resistance using the microcontroller, we could know that the projectile is blocking the light beam and thus when to fire the second coil. Unfortunately, the digital pins in the Arduino can only detect changes in voltage, not resistance. So we're going to need some circuit to make this work. A really simple thing to do is use a voltage divider. A voltage divider is in its simplest form, two resistors in series with one hooked up to power and the other to ground. The voltage at the point between the resistors depends on the resistance of each of the resistors. The voltage at this point is equal to the bottom resistor's resistance, or the resistor connected to ground, over the total resistance, times the input voltage. Here I have two 1 kiloohm resistors in the divider. Using the equation, we have 1 kiloohm over 2 kiloohms times the input voltage, which I have set to 5 volts. This means that we should expect this point to be 2.5 volts, and sure enough, it basically is. The resistors in practice aren't exactly a kiloohm, they can vary up and down by about 5%, but the voltage at this point is close to what we expect. I can replace the upper resistor with a 100 kiloohm resistor. This means our equation becomes 1 kiloohm over 101 kiloohms times 5 volts, which is a very small number. And sure enough, this lowers the voltage drastically. Now I'll once again change the upper resistor, but this time with the IR sensor. Now since no IR light is shining on the sensor, we expect it to be roughly a megaohm. Our equation tells us this will make our point have almost no voltage, and that's what we see here. If I bring the IR light in and shine it on the sensor, we saw the resistance to the sensor decrease to a little under a kiloohm. Plugging this into the equation, the output voltage should be a little under 3 volts, and in practice that seems to be more or less the case. This is looking good, but we can vary the value of the bottom resistor to give us a larger voltage swing. If I change out the bottom resistor for a 10K resistor, this means that when the sensor is covered, this point will be at 0.05 of the volt, or basically 0 volts. And when it's receiving light, it'll be at a little under 5 volts, so basically full voltage. This gives us defined logic levels and therefore the ability to have the microcontroller detect when the sensor is off and on. Now if I point the IR LED at the sensor with a little bit of space in between them, I can detect when the bullet is in between the LED and the sensor by measuring the voltage at this point. That's the theory behind it, and now it's time to put it to the test. I'm using the same setup from last episode. Remember, when I press the button, the first LED will immediately come on, but only when the light beam is broken will the second LED be also turned on. I'm replacing the MOSFET and all of the old sensor setup with the new voltage divider we just created. If I power it up and press the button, the first LED turns on. If I break the light beam with my pliers, it immediately turns on the second LED. Even if I break the beam really quickly, the second LED still turns on. Breaking the beam with my pliers simulates the projectile breaking the beam by passing through it. I can remove the LEDs and connect the outputs of the microcontroller directly to the gate pins on the SCRs to control when to dump power into each coil. Of course, for that though, I'll need a place to mount the coils and the sensor setup. I made this barrel to test with. Basically, I wound 2 coils around a couple of straws that I taped together. I can place the barrel of the gun between the sensor and LED so it can detect when a bullet is right before the second coil. I can move the breadboard side to side to either increase or decrease the distance the sensor is from the second coil to adjust exactly when it tries to fire it. For an initial test, I just want to try using the first coil, just for a standard of comparison. I'll charge up the capacitors to 250 volts in all of the tests. Since this is the same test setup as the last few episodes, I'll gloss over it a little bit. I should just be able to hit this button and activate the first signal wire, which will turn on the SCR. There is a small issue with directly connecting the microcontroller's output to the SCR's gate pin though. The gate pin on the SCR will rise up to about 250 volts or so when the main junction begins to let current flow. This will, and has, killed my microcontrollers. This was the microcontroller I was using last episode, and I fried it by connecting it to the gate pin. We need some way to isolate the high voltage side from the low voltage side. This can be done with an optocoupler. We're actually already using one of these, just in a little bit of a different context. An optocoupler consists of an LED pointed at a phototransistor. If the LED is turned on, the transistor turns on, and if the LED is off, the transistor turns off. Our projectile sensor works in a similar way, except instead of turning on and off the LED, we're blocking it with the projectile. This little package contains the LED and sensor. We can control the LED with the microcontroller, and have the sensor control the gate pin on the SCR. This means that the only connection between the high voltage side and the low voltage side is purely optical, and no high voltage can flow back and blow up my microcontrollers. I can install this pretty much by adding in a signal wire to the input side, and connecting the cathode of the internal LED through a resistor to ground. If I connected it directly, I'd probably overvolt the LED and blow it out. I'm also adding in a 150 ohm resistor in series with the output to limit the gate current. This might not actually be necessary, but I worry that too much current might break the optocoupler. To power the gate pin, I'm still going to use the 9-volt battery. These seem to have no problems in the past with the high voltage spikes, so I'll just keep using them. I just have to remember to hook up the negative terminal of the battery to the negative terminal of the capacitors. Now I can run my coil 1 wire to the LED side of the optocoupler, and when the fire button is pressed, it'll turn on the LED, which turns on the sensor, which turns on the SCR, and finally dumps the capacitor's energy into the coil. It works like this. Let's add in that second coil. I'll have to add in another optocoupler, SCR, and capacitor to control the coil. I can charge both capacitors up with the same high voltage board by connecting them in parallel, though it'll take twice as long since now I have twice the load on the high voltage board. Before I fire the gun, I'll need to disconnect the capacitors from each other. Leaving them connected will let the second capacitor dump all of its power into the first coil, which we don't want because then it wouldn't have any energy left for the second coil. I'll leave this clip lead on for charging though, and with that, let's start charging. Now with everything charged up, let's attempt to fire the projectile. Not bad. I've been adjusting the position of the sensor to give me the best launch, and I found about here's the best. That was a lot faster than just a single coil. I think with that, I'll end the episode. Next time I want to focus on improving the charging system and getting things ready to put in a shell. So guys, thanks for watching. Make sure to subscribe if you want to see the completion of the circuitry. If you have any questions or comments, feel free to ask below. Until next time.